Hello everyone, this is Sir Aris. Today, let's start our discussion with sections. Actually, this is supposed to be section 3, 4, and 5. 3, 4, and 5. So this is section 3 of chapter 6. So let's talk first about triple products and then differentiation of vectors and a little bit about fields. There are two products involving three vectors. One is triple scalar product. The answer is a scalar. And triple vector product, where the answer is a vector. For triple scalar product is written generally as for three vectors A, B, C, A dot B cross C. As a geometric interpretation, let's consider a parallelepiped constructed using A, B, and C as three intersecting edges. So our parallelepiped would look like this. So suppose this is our vector B intersecting with C on, say, the tail. Oops, suppose this is right like this. Okay, that's C. And suppose A is something like this. Okay. So our parallelepiped would be we can draw that by creating a parallelogram out of B and C. Suppose for B, it would look something like one side would look something like this, and the other side, let me draw a broken line because it would be found at the back. Okay. Connect a line parallel to B from the head of A, so it would look something like this. Okay, and then parallel line to A from the head of B, so it would look something like this. Parallel to C, we can have something like this. And so from C, we can connect a line parallel to A from the tip of C. So let's use a broken line. Okay, and then from tip of this intersection here, draw a line parallel to C. Would look something like this. And then from the tip of this parallel to A. And then from connect these 2 points, two edges here. Okay, so that's our parallelepiped. If this is angle theta, this would be B cross C. That's the area of the base. So BC sine theta, the magnitude of B cross C. The direction of B cross C, suppose this is a line perpendicular to B and C. So let's suppose that is our B cross C. So that's perpendicular to C, perpendicular to B. The magnitude of this is the area of this parallelogram. The height of the parallelepiped would be A cosine theta. So if this is phi. So if this is phi, we project that towards B cross C. That would be the area of our parallelepiped. So the volume would be base times height. So that's B C sine theta times A cosine phi, or BC sine theta is B cross C magnitude times A cosine of phi, or this is simply A dot B cross C. So the volume of the parallelepiped would be the triple scalar product A dot B cross C. We can write B cross C in determinant form. So B cross C is written as ijk on the first row, bx, by, bz on the second row, cx, cy, cz on the third row. We take the determinant, that's the value of this vector product. We can also write A that B cross C as AX times the X component of B cross C plus AY times B, the Y component of B cross C plus AZ, Z component of B cross C. This B cross C X component would be derived by taking the I component corresponding to this I hat here. That would be BYCZ minus BZCY. So this expression here is similar to this determinant by replacing AX, I hat by AX, J hat by AY, K hat by AZ. So we can also write this in determinant form where we have AX, AY, and AZ in the first row, BX, BY, BZ second row, CX, CY, CZ on the third row. For determinants, if we interchange rows, let's say we interchange A and B, we get the same result but with a different sign. So which means that if we write A dot B cross C and you interchange, for example, A and B, so that you have B dot A cross C. So that means we interchange the first row and the second row. We will have a change of sign, so we'll put negative here. Okay. Similarly, if we interchange A and C, that be C dot B cross A, but we interchange two rows, so we'll have a negative sign here. Lastly, say we want to interchange B and C. So this is obvious. This is a cross product or vector product. We change the order, we get negative. So negative A dot C cross B. Similarly, we can interchange two variables here, and then that would again give us a change in sign. So the overall sign would be positive. For example, you have let's interchange these two. So you have B dot C cross A. So we interchanged basically from the original form here, or here in this determinant, we interchange rows twice, so the overall sign is positive. Okay, B, second row we put in the first row, and then that first row we put on the third row. So third row gets placed on the second row. Okay, we can also interchange this B and A here. So you have C dot A cross B. Okay. If you interchange these two, we just get back this. Also, the dot products here, the orders doesn't matter. For example, this A dot B cross C is just equal to, so this is just equal to B cross C dot A. Okay, so the dot products, we can also do the same for the dots here. You interchange the sequence, it is just the same. Now, compare this with this. So this one and this one, they are actually equal, but the cross and the dots are not placed in the same positions. So these are ordered differently. So it actually doesn't matter. It doesn't matter where the dots and crosses are. So if you say, sometimes triple scalar product is often written as ABC, for example, it means that you have A dot B cross C or A cross B dot C. It doesn't matter. Both have the same magnitude, or just will give us the same result. Let's proceed to triple vector product. It's written generally as A cross B cross C. So take note of this parenthesis. This is relevant, which means that we need to operate this. It is generally not equal to when A cross B is done first cross C. Consider the following facts. B cross C is perpendicular to the plane B and C of B and C. So A cross B cross C is perpendicular to A and B cross C. So we are more interested in this part here. So any vector perpendicular to B cross C lies in the plane of B and C. So if you make a plot or a figure for that, suppose this is B and suppose this is C. Suppose this is the vector B cross C, perpendicular to both B and C here. So if we take cross product of some vector A with B cross C, it is perpendicular to A and B cross C. So if it's perpendicular to B cross C, vectors perpendicular to B cross C would lie along this plane containing B and C. So generally, we can write A cross B cross C as a linear combination of vectors B and C with coefficients A and B we want to find. We can get this A and B by explicitly expanding the components, where we can show that A cross B cross C equals B A dot C minus C A dot B. To easily remember this, it's sometimes called the back cab rule, where you have B and C, our vectors. The coefficients A and B would be, for example, B, it's the dot product of the remaining vectors A dot C. For C, it's the dot product of A dot B. And it's always that whatever is in the middle will be positive. The other one is negative. So let's now proceed with differentiation of vectors. If A is given by this expression, I hat ax plus j hat ay plus k hat az. I, j, k are fixed unit vectors. Ax, ay, az are functions of t. Then we define the derivative dA by dt by this equation, and it can be easily proven that if you have a scalar times a, you take the derivative, assuming a is a function of t also, you have dA by dt times a plus a times dA by dt. If you have a dot product, you have a dot dB by dt plus dA dt dot b. Cross product, you have this, a cross dB dt plus dA dt cross b. Dot products here, you can interchange, but the cross products of two vectors, the sequence cannot be, if you interchange them, you need to change the sign. In polar coordinates, consider, instead of using I and j unit vectors, let's use r and theta unit vectors. So it's denoted here as er and e theta. So ER is a unit vector directed radially outward. So from the center, the origin, it goes outward. While theta is perpendicular to ER, directed counterclockwise relative to the x-axis, like here. Okay, so if you have a point, take note, if you move the point here, the direction of R changes and theta also changes, but R is always radial outward. Theta is always counterclockwise perpendicular to ER. Similarly here. In rectangular coordinates, the unit vectors I and j are constant both in magnitude and direction. For polar coordinate unit basis vectors, they're constant only in magnitude. So the magnitude is always 1, but the directions change. So if you go from this point to this point, the directions of ERE theta would change. So in calculating the derivative, we must differentiate the basis vectors as well as the components. So if it can be shown that the unit vectors ER and E theta can be written as unit vectors I and j in this using this equations. So if we differentiate ER, say dER by dt, so that becomes I is constant I. Derivative of cosine is negative sine, negative sine theta d theta dt plus j sine theta, so cosine theta d theta dt. Or you can factor out d theta dt. That's minus I sine theta plus j cosine theta d theta dt. Or this is actually E theta hat. Similarly, for E theta, you have minus I derivative of sine, that's cosine theta d theta dt. And for here, you have j negative sine theta d theta dt. So you have here minus I cosine theta plus j sine theta d theta dt. Okay, so this I cosine theta plus j sine theta is just this. So that's negative E R d theta dt. So for example, given A, you have components here and the unit vectors. The components are functions of t. Find dA dt. So dA dt, you have derivative of product. So you have, say, ER, keep AR fixed. You have dAR by dt. Keep AR fixed. You have AR dER dt. Similarly here, you have E theta dA theta dt plus A theta dE theta dt. So let's use our formulas for dE R dt. dE R dt, that's E theta d theta dt. So here we'll just copy here A theta. We'll use this. dE theta d theta, so a dt, but there's a minus sign, so we'll put negative here. So ER d theta dt. Okay, so that's our value for dA by dt. Okay, a little bit about fields. If you encounter the word field, there are two types. So the term field is used to mean both region, so the position, so the region can be described by positions on this region, and the value of the physical quantity. So there are two types, scalar field and vector field. If the physical quantity is a scalar, we speak of a scalar field, for example, temperature. So if you have a certain region where at each spot the temperature, so for example, this is an XY coordinate system, maybe at some point there's a temperature T1, at another point the temperature is T2, at another point the temperature is T3, and so on. So any position on a certain region, certain positions will have specific value for the physical quantity. Okay, for temperature, it's just a scalar quantity. It doesn't have directions. It only tells the magnitude. So it's a scalar field. So another case is that of a vector field. So if you have an XY coordinate system, and suppose, for example, if you have vector quantities like electric field, force, or velocity, at certain positions, there could be a specific, say here, there's an electric field directed, say, in this direction. Let's call that E1. But at a different position, the electric field changes to, say, here. Okay. And a different direction here, or a different position, the vector is also could be, let's say, different. So there you have a region and you have assigned vectors on certain points. So in this is called a vector field. The first one is called a scalar field. So we'll discuss more on this about this in the next section.